Thanks for joining us today, guys. Appreciate your time. So just a quick round of introductions. My name is John Hanzelka. I'm Technical Art Director for the Endava Synthetics team, joined today by Jacob. I don't think you have a mic right now, but Jacob Berrier. He's a senior technical artist with our team. I also want to give a shout out to Dan Shu, who's responsible for doing all the machine learning work that we'll be showing today. Tidy in the front row here, who did a bunch of the Houdini pipeline work as well. So just to give you an overview of what we're going to be talking about today, we're going to start off with a quick intro about who we are at Endava. Then we're going to go into a crash course around understanding machine learning and how synthetic data applies to that. And then we'll dive into an internal use case study we did for dental X-ray analysis and how we can apply these concepts to a unique domain or a unique spectrum, as the title suggests. So we'll go through the Houdini workflow for that, and then we'll talk about how we translate that into the process of training a model and evaluating results and iterating. So just to get going, who are we? Endava is a global technology services company. Been around for over the past 20 years, locations across North America, Europe, Latin America, and Asia Pacific. Really the company's focused around reimagining or re-envisioning the way that people interact with technology. And as part of this, we've had the opportunity to work with a really broad range of industry verticals and just use cases for machine learning in general. So to cover some of those, oh wow, this is animated. I actually didn't know that. But to cover some of those, Endava's historical main focus area has been in financial, payments, and banking, but we have significant presence in areas like retail, healthcare, gaming, and media. Having such a broad range of customers has really shown us firsthand how the struggles around collecting good training data to train your machine learning algorithms and really achieve the level of performance you need to deploy a model into a production environment. Due to this, it's inspired us to start up this synthetic data generation effort, which Jacob and I and other folks on the team are a part of. Given that we work with so many different industries, we needed something that was, or a pipeline that was highly adaptable to each new use case. We didn't want to be reinventing the wheel each time we took on a new customer. So our first focus was really about standardizing our pipeline, ensuring that we could get quality machine learning results from it, and then enabling us to scale through Houdini artists that are capable of doing this stuff on a day-to-day basis. So I'm going to give you a painfully oversimplified explanation of how machine learning works. If the past week at Xrays been any indication, it's a space that's evolving very quickly. Everyone's really excited about it. I'm going to be talking specifically about an area of machine learning today called supervised learning. And to be even more specific, supervised learning for training computer vision models. And so let's talk about donuts, which I hope is where you expected us to be going with this talk today. So with machine learning, we can think of the neural network like a brain that we were trying to teach things. With supervised learning, we curate our input with two types of input. We have images, in this case of donuts, with different types of variability represented within there, and then a set of annotations that tell our brain that these are pictures of donuts. Our goal with this is to achieve enough diversity and variability in the input that we put into our model that the neural network starts to kind of generalize the concept of what a donut is. When presented with a new donut then that's never seen before, it can still say, hey, this is a donut as well. Again, oversimplified, but that's the high level. Now, the annotations that we feed into our model are commonly referred to as ground truth. Depending on the type of ground truth that we present our network, we can achieve different capabilities in the vision space. These capabilities range from simple operations like classification, where the model can identify the images or the objects that it's seeing the image, scaling upon that to detection, where it can say specifically where in the image these objects are, and then a step further, actually drawing polygonal segmentation around where those individual pixels are. More advanced capabilities include things like understanding, where the model starts to interpret specific properties of the object, like in this case that the donut has a bite taken out of it. Targeting, where we can understand the 3D position in real-world space of an object. And then finally tracking, which we can interpret the motion properties of the object. Not the best example, donuts don't have skeletons, but this, hopefully you can make the mental leap to kind of understand that. So now that we have this basic ground level understanding, how do we apply synthetic data in this space? The easiest place to start with that is to understand some of the challenges associated with machine learning. This is just a subset of these, but they are ones that we encounter on a frequent basis. So first and foremost, one of the biggest challenges with machine learning in general is just the case of rare data. Collecting enough quality data to represent all the diversity that you would need in your data set to train an effective machine learning model is really difficult. Scarcity can be encountered for many different reasons, but in a lot of cases, this is simply due to the fact that the thing that you're trying to detect or understand may not happen that often in the real world. This is really common in cases of like safety inspection or industrial manufacturing, where it may not be ethically plausible to do a staged collection of this, or it's just not financially viable to try and do this either. Synthetic data can fill these gaps and enable capabilities that would not otherwise be possible. Privacy protection, I think most of us are probably aware with the challenges with using personal information when training a neural network. We can get around these by using things like 3D avatars, where we don't have to ever infringe on people's personal information. Data precision, as the saying goes, garbage in, garbage out. The quality of your input into a machine learning will play a direct role in how well it performs in the end. When synthetic data is done right, we can get pixel perfect results that are consistent from frame to frame. And it also enables a level of precision that's not possible to be labeled by humans, such as the joint positions within a hand, for example. Pre-visualization, synthetic pre-visualization is commonly used in hardware development, where the device that you're producing may not actually physically exist for years to come. So it allows you to plan ahead and start algorithmic development long before the factory line ever starts pumping out these devices. Reproducibility, synthetic data can be generated on demand and can evolve with your project as updated specs come along. And then generalization, which in a lot of ways ties back to the rare data case, where just getting enough diversity in order to allow your model to generalize into a broad application tends to be very difficult. So synthetic data, let's define that. In the case that we're talking about it today, I will refer to it as artificially generated machine learning data, training data that mimics the characteristics of a real world phenomena. In layman's terms, we make a donut in Houdini and we render an image of it. But as I mentioned before, the image is just part of the story when it comes to synthetic data. It also comes down to the ground truth or the annotations that we're including with that. When we generate synthetic data, we include these annotations in a JSON file that gives per image annotation information about each one of the images that we're representing. This is where we include information about the bounding box, the segmentation, the label, so on and so forth. We tend to use the COCO standard for doing this for many different reasons in terms of like extensibility, which Jacob will cover a little bit more, but just as well as how widely used it is with many different machine learning architectures. It's easy to output this directly from Houdini and just start a training process right after that. The cool thing about this really is that in most cases, this is information that already exists within Houdini. We just manipulate it in a way and expose it that can be directly consumed in our training pipeline. So as an example of this, where these differences kind of show themselves when it comes to the things we're accustomed to as 3D artists and technical artists and how they need to go into machine learning pipeline. We see on the left here a skeleton as it would typically exist in any animation pipeline, the joints associated with that. And on the right, we have a very commonly used key point annotation segmentation or key point location skeleton for doing pose prediction of a human. There are similarities here, but there's also fundamental differences in allowing the artist who is producing this scene to understand what this information is being looked like from a visual perspective, as well as the metadata that's being passed on really helps with kind of some of those things we mentioned about garbage in, garbage out. The earlier in the pipeline you could diagnose how your ground truth is looking, the more effective it's going to be when iterating and improving your results. So back to donuts. As I mentioned before, the benefits of having a programmatic approach to ground truth generation can be represented in these two images where we've overlaid the Cocoa JSON on top of the image. This is just using a Python library called 51, which is super handy. On the left, pixel perfect animation or annotations. You can see down to the individual sprinkle. We have a very, very accurate and consistent segmentation mask, and then complex annotations where we are isolating the icing as its own class. Asking a human to label thousands of images at this level of detail, as well as consistency, is really not feasible, let alone in terms of like maintaining accuracy, but also just the sanity of that person that's being asked to do this task. Next, variability. Any Houdini user should be very familiar with this concept. In synthetic data generation, we use variability as a way to inform the model of the things we want it to learn. So in the case of our donut, for making a generalized donut detector model, we'd want to embed some basic types of variability, like maybe different icing colors, different sprinkle types, different backgrounds, different camera angles. A lot of these are very basic forms of variability, and depending on the scenario, they can get more and more complex as you scale upon these things. Having the ability to control these aspects is a big role in achieving the quality of distribution that you need in your data set. So keeping going and doubling down on this culinary theme that I've gotten myself onto here, I like to think of a data set as a mixing bowl in a lot of ways. And depending on how we combine our ingredients is going to directly impact the quality of how it gets trained against in the model. I like the ingredients are really the tools we have within Houdini to produce procedurally varied elements, photorealistic lighting, things like that. And the recipe is how we choose to combine these elements into the resulting data set. And the way we combine these plays a major effect on the results of how our model can perform. In this fictitious case here where with our donuts, if we were to represent certain types of donuts more commonly in our data set, so in this case, pink frosting with rainbow sprinkles, our model is going to associate those features more strongly with the donut class, and we may end up unintentionally bias our model. This is not the easiest, or the most applicable application or explanation of this, but we've encountered scenarios like this in the past on past projects doing things like airplane detection and classification, where initially our model distribution was biased towards a very specific plane model. When we trained the model on that, we could detect the airplanes very well, but we had very frequent misclassifications because we had overrepresented a specific class of airplane in our data set. So being very intentional about how you structure the distribution in your data set is very important. Moving on, talking about the comparisons between the training workflows with real data. Well, the point is they're not that dissimilar. With real data, you collect pictures of real donuts, you label those, you train your model, and you evaluate the results. With synthetic data, we develop a pipeline that enables us to produce this procedurally. We generate the data using a render engine, train the model, and we evaluate results. The major difference comes in when you start to evaluate the time to iterate. With real data, something like 80% of your time is spent just collecting and labeling the data. When hardware changes come online or a use case is modified, it could potentially lead to needing to totally scrap your data set and start all over with collection. On the other hand, with synthetic data, we make an upfront investment into a pipeline that allows us to generate this data at scale. As the pipeline is used, it becomes more mature and iteration times speed up. If a hardware change comes along the way, we're not starting from scratch. We update the camera intrinsics that we're using on our model or on our camera, and then we regenerate the data with all the capability that we've already introduced from the start. Okay, so getting back to the topic at hand, what do we mean by beyond visible light? As most of you are probably aware, lighting is a type of electromagnetic radiation that exists on the electromagnetic spectrum, which encompasses a really broad range of frequencies and wavelengths. The very narrow band in the center there is the portion that you and I can perceive with our eyes. Outside of this visible band exists a wide array of different camera and sensor types that we can develop machine learning solutions for in the same way we do for the visible light spectrum. Some examples of this, starting from the far right, I guess, would be thermal imaging, which is commonly used in medical diagnostics and building inspection, search and rescue. Near IR, which is often used in low light or no light conditions, such as security camera systems, wildlife research, many different cases for near IR. Ultraviolet, which is used in forensics and law enforcement, scientific research, and then X-ray, which we will be talking about today, which is commonly used in medical imagery. The interesting thing about these non-standard domains is that all the challenges that you have with collecting data in the visible light spectrum are often compounded in these alternate domains, just because they become even more difficult to collect the right distribution of data. So now let's cover dental X-ray analysis. You might be wondering why we chose to do dental X-ray analysis. Believe it or not, Jacob and I are not dentists. So forewarning for that. But prior to this, we really didn't know much about dentistry in general. But fortunately, we were able to work with Jacob's dentist, Dr. Paul Amato, to get a lot of really valuable insight into the clinical approach and process of both collecting and analyzing X-ray data, and his feedback on our imagery as we iterated was really valuable in just structuring the whole pipeline in general. Really, the goal with something like this is be able to take the domain knowledge of an expert, like a dentist, who understands, when I look at an X-ray, this are the things I'm looking for, and be able to try and translate that into a way that a machine learning algorithm can kind of derive that same information. Prior to being in Endava, Jacob and I spent the better part of 7 years at Microsoft iterating on these same types of problems and dabbled in this space before. So as we've been building our new pipeline, we've been looking for difficult cases. X-ray is a fundamentally different way to approach content because you don't care about the exterior of the object, you care about the things that are going on inside of it. Which really differentiates it from something like IR, which in a lot of cases can be achieved by material and texture and lighting setups. So it was kind of a new way to frame an approach to synthetic data and a challenge to see if we could achieve this in a reasonable manner. There are three types of X-rays that you may be encountering in your dental visits. Panoramic X-rays capture a broad view of the full mouth. And bite wing X-rays capture the back teeth, upper and lower. This is the X-ray where they put the piece of plastic in your mouth and make you bite down. And then periapical X-rays, which capture the full tooth from crown to root tip. For the purposes of today's presentation, we're going to be focused on bite wing and periapical. But it's worth mentioning that a single synthetic data solution can be produced for all three of these domains, which is another really valuable aspect of synthetic data, where you're not starting from scratch each time you have a new use case. So the things we're going to be trying to detect are not only the teeth, but also different types of defects. There are a number of different defects we may target as part of this. We're going to be focused on fillings and cavities. Fillings occur as a bright white spot or bright mass inside the tooth. Cavities are a void that gets created. But other cases exist that kind of can extend the usability of a solution like this in an actual clinic. So root canals, which are where the inner pulp has had an infection and been treated, and then decay, which appears as a dark mass as an infection in the bone. So if we liken this scenario back to the machine learning challenges we discussed earlier, you can see how well these align with some of these cases. So rare data, there's a lack of general available data to be able to train a model with in this domain. And the public data that is out there is generally a very poor quality as well. And this was a challenge that we had in just doing this project because we had to collect enough real data where we could validate the performance of our model. So in addition to that, there's just limited availability of X-ray capture devices. You can't just pop down to your local dentist and get some photos whenever you want to. So it's expensive devices that are not readily available. Privacy protection, I think we're all aware of HIPAA laws associated with protected medical information. Generalization, being able to collect enough instances of these conditions to capture all the variability, not to mention all the variability in just the human population, is very difficult. With synthetic data, we can create this as a programmatic process. And then, addition to that, like X-ray devices are going to vary from capture device to capture device. Some may have higher intensities, some may have different types of noise. So this is just a compounding problem that gets harder and harder. And then data precision. And this goes back to why we needed to work with Jacob's dentist, because we as non-dentists don't understand the nuance associated with these, and we need to capture that nuance in order to be able to accurately train our model. And finally, what is the value that can be brought with something like this? So the goal here is obviously not to replace dentists, but by handling routine analysis and highlighting areas of concern, these systems can really free up the professional's time to spend more time with their patients. So things like analysis assistance, where it serves as a second set of eyes for the dentists, can save time when they're actually consulting with their patients. Processing this information at scale can, again, reduce the amount of time needed for routine analysis. And then the third area where I think is the most beneficial when it comes to just dental analysis in general is the ability to detect difficult to detect cases early on before they may be visible in traditional methods. This early detection can really lead to better patient outcomes long term. So with all that boilerplate information, I'm going to hand it off to Jacob to talk about how we approached this in Houdini and generated this data. So go ahead, Jacob.
Hi. So just a quick overview of our general pipeline. Making synthetic data is not really all that different from most rendering pipelines. We make some stuff in Houdini, then we render it. The key difference is generating a lot of variation to generalize the data set. PDG is great for that. And then the other difference, like John said, is the annotations that come along with it. So we've made a few tools to help extend the capabilities of Houdini to more easily facilitate generating synthetic data. We classify these in a few different sets of things. Tools that we use for every data set, things that make labeling easier and post-processing, some basic compositing tools, and then just general workflow automation. Then some tools that are more specific, like help with key point annotation in a crowd or with a human. And then scenario-specific tools, things that are custom to every pipeline, and things that would be difficult to label as well, such as the area that a vehicle has been damaged. And this is generally where we spend the bulk of our work. Speaking to the radiographs and X-ray pipeline in general, fairly basic setup here. We did make this in about a month before SIGGRAPH, so this entire pipeline is relatively early in its stages. But we have a couple purchased assets, the skull and the teeth that we obtained externally and just cleaned up to prepare. Did some math in SOPs to generate the internal anatomy that you see with an X-ray, as well as the defects. Then added variation to all of these that's driven by PDG. And then the X-rays are very simple volumes, unlit in Karma. And again, just covering like, what's a little bit different about this is we're generating data to generate ML rather than using ML to make renders or other normal pipeline stuff. So to start, we took some teeth that John then sculpted in Blender to make a set of baby teeth and adult teeth. These are then compiled as blend shapes and SOPs. And this lets us vary the size and get more variation out of a single set of models. This ensures anatomical accuracy as we randomize things and allows for different stages, or allows us to show different development stages of teeth. Next is how do we replicate the internal anatomy of a bone or the biology of a bone. There's things called osteoclasts and osteoblasts in the bone. These are represented as higher and lower densities. Osteoclasts is the new bone that's growing. Osteoblasts is the old bone that's your body is removing. And the osteoclasts show as higher densities while the osteoblasts are lower densities. And this really as an artist, this just translates to a bunch of layered noise with find shortest path as well. So it's just kind of some artistic interpretations of looking at a lot of X-rays. The next set is the tooth anatomy, which consists of 3 layers: the enamel, the dentin, and the pulp. And to get this, we made a custom peak node that just has a ramp to fall off, and these are manually set for each tooth. And then that's varied along with the blend shape as well as the size of the tooth. And it's randomized a little bit in a range with PDG as well. So to continue the variation and adding more generalization to things, since we only have one input of a single skull and a single set of teeth, we need to get a lot of different variants out of that. So adding things like positional change in the teeth, shape variation within the teeth, bending the roots, density variation of the X-rays, and jaw rotation for things like bite wing enable a much better generalization and start to expand into a wider population. And the way that this pipeline is structured and built allows for the addition of more skulls and teeth in the future. The two main things that dentists use to identify teeth numbers is the shape of the root, the way that it's bending, as well as some subtle variations in the upper and lower jaw. And so these other variations will help the machine learning pipeline focus on those to identify the teeth numbers as well. Next, we add some basic defects. This is pretty basic Houdini stuff. There's a scatter with a copy to points. My lumpy spheres aren't quite as good as Rich Lord's, but the only main thing to note here is cavities generally only happen above the gum line and on the distal, mesial, and occlusal parts of the teeth, which simply means that top and sides. And this is part of the feedback from the dentist and working with him to understand, how these things anatomically happen. Initially, I had cavities and fillings on the roots. That doesn't happen. The next thing is understanding how radiographs are captured. The radiation source is placed on the outside of your mouth and the sensor on the inside. This can introduce some variation if it's not placed quite correctly. You'll get some interesting distortions from that. Or if the radiation source and the sensor are misaligned, you'll also get distortions from that. It's kind of like using a large format camera, if anybody's familiar with that, if you offset the film plane and the focal plane. So there's, again, this pipeline from a Houdini standpoint isn't the most complex. I just took the centroids of each tooth, resampled the curve, and then there's some jitter and random orientation to account for camera distortion. Again, it's just kind of another or more visual examples of that. One of the things that came about from revisions on this is there's no optics, so using an orthographic camera kind of resolves that. And then understanding that the sensor is on the inside of the mouth and not the outside makes very subtle differences and really messes with the tooth identification or tooth classification, because then the roots are backwards. Next, showing some of the tooling that we've made for this that enables easy labeling and easy setup for labeling the different parts of the tooth. So we have a Cocoa data node that is really pretty simple. It just makes Houdini attributes that we have set up that are read by Karma and rendered as a custom AOV, and then the Cocoa JSON that collects all of these and writes out the JSON that's associated with the render coming from Karma at the same time. And this is an example of that. It's pretty much just an object ID with some text and a description along with it. These are very explicit IDs that are associated. So when you assign things with the labeling node, it just assigns a very specific value in the object ID. And then there's a visualization of that. So you can see the different masks for the different cavities and fillings. Then we have kind of a basic framework that helps automate a lot of this and streamlines the process of setting this up. There's a lot of repetitive things, setting up basic seeds and wedges from PDG, adding variation per frame or per variant. So you could have, if you want sequential data, you can vary things per frame, and then you have different variations of each of the sets of frames. The Cocoa JSON output, and then the render wrangling and AOV combination. In this case, there's a separate step for having different AOVs as the different objects overlap, the cavities inside the tooth. So if you try to render that as just a generic object ID, you'll just get the tooth. And then image post-processing, and finally annotation aggregation. A lot of this structure helps us just quickly start a pipeline, and we know that everything will be set up and the output will work with the machine learning pipelines. So save some steps there. One of the components of this is just image post-processing, pretty basic compositing things. This just adds another level of variation to things and helps us model the sensor characterizations more specifically. So a lot of the noise that you see in a radiograph and other sensors or lens distortion, things like that. The most common scenarios we use is just noise, color correction, sort of matching the sensor as closely as we can. Beyond that, we do what's called data set abuse, where we just will randomly add things, controlled randomness, smearing different images over it. And this can help focus the neural network in the training pipeline in the ways that we want it to. This is an example of the final Cocoa annotations. All this simply says is, hey, in this render, there's these pixels are tooth 1 or tooth 2. And what's kind of nice about Cocoa is we can add any attributes that you want, anything that's in Houdini's metadata, things that would be difficult to collect in real data, like if you want to predict forest fire movements from satellite data or something like that, you could add wind direction or like fuel sources or things, anything that you would have in the PyroSim. And so, yeah, this just makes that really easy. This is the final example of one of the data sets or sampling of the data set. And on the right, we have on the left, we have the renders, and on the right, the visualization of the annotations. And you know, I mean, it's sort of like CryptoMat that's optimized for machine learning. Yeah, this pipeline, once you set it up, or once we had it set up, we made several iterations to help improve the machine learning. And that's kind of a back and forth that you do that makes it a lot easier to generate and make changes. So, yeah. John's going to go over the machine learning side.
Cool. Yeah, so once we have our data set, we can start to enter in a cycle of doing model training and evaluation. We could probably spend an hour alone just talking on this. I'm going to be distilling down a lot of the great work that Dan did on this pipeline. So it's a complex area that I'll try and summarize for us all here today. So first step in the training process is really to identify the architecture that we're going to be using for this process. For this particular case, we used Detect as our architecture with a backbone of ResNet 101, and then trained, I think, Solove 2 from scratch off of that. The other thing we need to consider as part of this as well is how many images we're going to be using in our training pipeline. We found that with as little as 500 images, we could get relatively decent results, but in order to not overfit on our data set, we had to introduce a lot of image augmentation along the way. I believe in the end result, we ended up using around 4,000 images to train this model. In this case, 15 epochs of training, which just means full cycles of looking at our data set, training for 45 hours on a single GPU. If we look here at these two graphs here, we can see two things. First, on top, we have the loss value, which gives you a measure of how well the predictions align with the test set that we've provided our data set. And on the bottom, we have the mean average precision, which provides us an overall understanding of how the quality of these detections that it's making as well. So as these start to flatten out, it gives us an indication that the network has learned everything that it can from our data, and determining when to stop training is an art in of itself that is really in the realm of the machine learning folks. In addition to that, as part of our standing up our process, we need to set up our validation pipeline where we can start to interpret how well we are performing on data that's never been seen by the model before. Given the scarcity we had in real data, the first step here is really testing on synthetic data, which is an area you have to take with caution because it's not necessarily a direct indication of how it's going to be performing on real data, but it can at least give us an understanding of whether or not our model is able to learn anything from our data whatsoever. So it serves as a good analog for us along the way to be able to kind of start experimentation in these early stages. I'm not going to dive too deeply into the metrics as part of this really, but just to give you a sense of the information that we're looking at when we're evaluating the quality of the model, we can look at the output from the training pipeline and start to interpret some information from what these metrics look like. So if we look at this, we can see with cavities here that we do a relatively good job of detecting the cavity, but actually predicting the exact shape could definitely use some improvement. When it comes to the fillings, we do a pretty great job of finding them every time, but certainly predicting the shape could be done better. And then with the tooth, we do a great job. We can detect them and we can predict the shape very accurately. Their overall mean value in the lower right, this gives us kind of a metric or a number that we can use to compare data set to data set or model training to model training to kind of evaluate iteratively how we are performing as a single metric. So as I mentioned before, this is on synthetic data and it doesn't really tell the full story. The only way you can really start to understand this is by transitioning to real data. And when we did that, nothing worked. Which, honestly, like this initial failure is very common when it comes to machine learning, even on real data. If we look at these images here, we can see like we're missing teeth all over the place. Our segmentation masks are very incomplete. We're getting multiple teeth detected on single teeth. So there's just, it's a mess. But again, like this initial failure is really common. And I think in some cases, this is where synthetic data may get dismissed as a viable solution to machine learning. But in my personal opinion, this is where the actual work begins. Once we have stood up a pipeline for generating data in Houdini, been able to establish a baseline with real data, we can start to iterate. And really one of the fundamental places where issues like this occur is this dreaded thing called the domain gap, which very scary graphic, I know. But so you can think of the domain gap as the discrepancies that exist between the synthetic data that we're training with and the real data that we're validating against. Understanding this gap is key to being able to, allow your model to generalize from the synthetic world into the real world. I, as a visual effects artist, like to think of the domain gap as kind of everything that happens from the point of the image coming out of the render to making it into a final shot in the film. So this is things like color correction, camera sensor characteristics, blur, noise, background compositing. All of these elements can play a major role in better aligning and marrying our data with the real world, which in turn will help our model learn. Inherently, synthetic data is perfect. So in a lot of cases, what we're doing is actually just dumbing it down to be more aligned with reality. But it goes beyond just the visual aspects as well. The machine learning algorithm does not care at all about the aesthetics of our image. I like to say, like, I don't care what you think of my art, the computer likes it. So, and that's really what we're doing here. We're making imagery for a machine. The machine is our audience here. So because of that, we need to understand like what cues or what information it's identifying and trying to learn from. And this, in my opinion, is where synthetic data is really the sweet spot in between visual effects and data science. It's a collaboration between disciplines, and I think each one brings their own kind of specialization to this world where visual effects artists are very adept at building these procedural pipelines that can generate thousands and thousands of images. They understand how to visually inspect an image to identify like where areas could be improved. Conversely, the data scientists really have superpowers when it comes to doing large-scale analytics on data and identifying both like statistical and qualitative information about how we can better align and better adjust and better produce the data for the network to learn from. And so this is, when we combine these two disciplines, this is how we start to approach this problem. So if we look back our iteration loop, we are right here on the blue dot at the evaluate stage. This is where we have trained our model. We have some initial horrible results, and we need to figure out what we do to improve it. Careful concern needs to be taken here in terms of the choices you make when iterating. If you do too many things at once, it may be difficult to track back and understand, hey, what helped or what hurt. So this is where we really are very iterative and very intentional about the things we introduce in our data set day to day, or data set to data set. In this case, we were iterating on a daily basis, but it's really one of the powers there where you can be very, very methodical about how you're producing your data sets each time. So the first step was kind of a data analysis step to compare the synthetic data set to the real world data set. And this is some great work that Dan did to just analyze it at scale, like what are some of the fundamental differences between the real data and the synthetic data. And when we started to look at this, some of the first things we noticed were that, hey, like our luminosity, as well as our histograms on a per image and per category level were subtly off, but these subtle differences can play a major part in how you generalize to real data. So in order for us to address this, we went back into Houdini. We made some adjustments on density values. We added some gamma adjustments as a post-process step, and then continued to iterate. In addition to the augmentations or the modifications that we made on the training pipeline, we also added in augmentation steps as part of the machine learning process. There's a really great Python library called Albumentations that we like to use for this that can probabilistically, I think that's the word, introduce different variation into your data set. So things like random brightness, blur, cropping, and whatnot can add more diversity into your model and can help it focus on the things that you're trying to teach it. In a lot of ways, machine learning algorithms are lazy. They're going to try to find the path of least resistance to say that they've learned something. So if we can make it in some ways more difficult to learn from our data, we can focus its attention on, say, like the shape of the object as opposed to the context in which it's seen. So these are considerations that we take as we iterate. And if we look at the time box iteration we gave ourselves in a 2-week time to improve these results, you can see that in the early stages, we're doing very broad sweeping changes to how we're producing the data. We're fine-tuning the shapes of the teeth. We're tuning the densities, widening gaps between the mouth. As we progress into the middle stages, we're being more specific and targeted about how we make adjustments as we start to better understand how the machine learning model is performing. And then finally, in the very last stages, we're doing very minute tweaks. Like dataset 9 and 10 was all about just getting the right jaw rotation because the network was classifying upper and lower tooth as a single class or a single observation. So we needed to have better variability in how we presented that. And you can see this progression through these images here as we work our way through the dataset generation step. In dataset 1, all hope is lost. Our SIG graph presentation was going to be ruined. Data set 5, we're starting to see slow progress. There is some hope. We're starting to better understand the shape of the tooth. We don't have as many, multi-classifications on a single tooth. And then in data set 10, where we've clearly learned the shape of the tooth, and we're starting to make predictions about where cavities and fillings exist. So it always feels like it's always like the last 5% of the effort is where all the work goes, and that's in this case very much true. So this improvement can be seen when we look at the wider validation set as well, where we're no longer missing teeth classifications. In general, our segmentation masks are much more complete, and we're getting detections across the board for where the model thinks it sees cavities and fillings. Now, these are Jacob's X-rays, and he does not have this many cavities and fillings. So there's a lot of false positives in this. But the interesting thing here is that if you look at the confidence value, or how confident the model is that what it's predicting is actually a cavity or a filling, the vast majority of these false positives are very low confidence. So in this case, the one I'm highlighting here, I don't know if you can see that, but it's 30% confident. So by even just fine-tuning the parameters of our validation pipeline, we can weed out a lot of this noise and get much more consumable information from it. And this can be seen here in this case of the one actual cavity we have in our validation set, where the cavity is being predicted, the shape is relatively accurate. Confidence value is only 65%, but it's distinguished or differentiated from the false positives. So this is indication to us in these early stages that yes, we can train the model to understand these things, and through the course of additional iteration and fine-tuning of how we represent the data, we can improve these results and have a more effective pipeline. The thing I'll mention here, though, is that, to me, this is the magic of synthetic data. The fact that Jacob and I can make some images that suddenly translate into, machine learning that can predict these things in the real world using, clinical knowledge it never ceases to amaze me, and it's something we should all really care about, because it's a really growing industry for applying, visual effects artists' skill set to this domain. So it's like black magic in a lot of ways. But again, these are the initial steps of this pipeline. We had a time-boxed amount of time to put this presentation together. If we wanted this to be something that we could deploy into the real world, there are additional steps that we need to take. So first and foremost, we need to acquire more quality real data. We want to be able to validate at scale so that we can have the confidence to say to a dental clinic that you will achieve this level of accuracy, and we will not be bugging you with all these false positives along the way. So that goes hand in hand with the performance improvements. As we get informed by the quality of real data, we can adapt to that and perform our overall quality of our data. Next, we need to expand the scope and diversity. As I mentioned, there are a number of other cases that we can expand into in terms of root canals and decay and other higher value conditions that may occur in a patient, as well as input diversity. And Jacob touched on this as well. We're using a single skull with a single set of teeth. If we want to ensure better generalization across the entire population of planet Earth, I guess, we need to have more variability there. And then lastly, more advanced ML features. There are additional value that can be brought through the capabilities of this network. So things like actually predicting the tooth number in addition to just the fact that it's a tooth, as well as much more difficult cases to predict, like resorption or cases of bone loss estimation in the tooth as well. So with that, I want to say thank you to all you guys. It's really exciting to me to see how synthetic data is being applied in such broad ranges now. There's amazing work being done around like self-driving and human-centric scenarios. That really the thing to highlight with this is that synthetic data can be applied in so many different domains that you may not have thought about. Dental analysis was not on the top of my list when I initially got into synthetic data, and it can be a really rewarding challenges to solve as artists, applying your skill to like real world problems that can improve the value of people's lives. So thank you very much. Appreciate it.
As far as I'm concerned, this is the most exciting use of machine learning in the future. I mean, today and in the future, is this application to healthcare, being able to analyze things more quickly and more accurately based on scans, which I hope become more easily accessible to everybody in the future, not just for dental, but for cancer and other healthcare-related things. I think it's really, really, really exciting, and I'm happy to see that Houdini is part of it and that you guys are tackling these challenging problems. So thank you for doing that, and thanks for sharing today. Questions? Yeah.
Hey, thanks for that. Is there any room in this loop for like domain expert human validation of this stuff? Or I know dentist time is expensive, but was there any thought put into whether or not you can have somebody just kind of say, you got this right, you got this wrong, and sort of get human labeling or input into sort of improving the model? Or does that defeat the purpose of synthetic data? Or
Well, I think certainly like through the course of this iteration, that was what we leveraged Paul Amato for, the doctor, because a lot of the early iteration we were doing as well was things that we overlooked. So, for example, one of his initial comments was like, "Your roots are way too thick. You need to adjust the sound." And me and Jacob wouldn't
Classic.
have known that. But it was interesting though. Like by doing that was one of the steps that really improved the performance of the model. So I think the human in the loop, especially when it comes to these cases where it takes kind of doctor level understanding, can really help.
cool, thanks very much.
This is how cold it is in the room right here. Covered in a blanket.
I've been shivering up here.
That was really interesting. Thank you. How much synthetic data do you need to generate to train your model?
Yeah, so for this case here, we ended up with about 4,000 images, but it's going to vary on the complexity of the case. Like some of the stuff we did, previously in former lives was, we were generating 60,000 frames a week, so it really depends on the problem.
And do you need to generate more than, like, let's say you had real X-rays? Would it be the same amount of real data that you would need to train your model? Or with synthetic data, do you need more images?
Are you saying, like, when you say real data, are you saying
Like
that
real
that's your...
X-rays. Like, let's say you weren't using synthetic data, but you were using actual real X-rays. Do you need the same amount to
Oh,
train?
I see.
Yeah.
That's going to depend on how diverse your real data is too.
Yeah.
And that's, again, there's plenty of customers we've worked with where it's like, we have a real corpus of data, but there are gaps in it. Like, for example, worked with a customer where they had a manufacturing line, and a lot of their defects, they had pretty good representation for, but there were some classes like, we have 13 images of this, so
Interesting.
you can augment, an existing real data set with synthetic
Oh,
data
so
set.
you've actually made systems with both real and
Yeah.
synthetic.
Yeah.
Yeah, often it is kind of a mixture, and you can use synthetic data to be more targeted about things. And we've had some instances where it's taken more real data than synthetic data, just because you can be more targeted about what you're using in the data
Right.
set.
The annotation system you have in PDG is super interesting. It sounds like it must save a lot of time. With the real data, do you have to do that manually?
Yeah, so labeling real data, especially with segmentation, there's several apps that are optimized for it, but it's effectively just drawing boxes in Photoshop and
Uh-huh.
Yeah.
Wow.
which is really
Yeah.
exciting for 10,000 X-rays going
Yeah.
cavity. So
Yeah, so this PDG workflow is pretty incredible for automation.
yeah, and if you think about that too, ask your dentist how much it would cost for them to sit and label a bunch of X-rays for the tooth numbers and draw masks.
Mhm.
So
Yeah. Thank you.
Thanks.
So you've mentioned combination of real and synthetic training data for maybe not for this example, but for other examples. And there's the thing of synthetic training data being very valuable for rare cases, where now you would potentially create the rare cases as synthetic. You would have no or very little examples in real. Have you looked into how well a model can then detect the actual case versus detecting that it is synthetic data, picking up on noise or something that makes the data like detectable in that sense? So where you then suddenly have these rare cases not detected by their actual real world characteristics, but by the characteristics of your data. That seems to be of danger.
Yeah. And I think this is, to me, this is where it kind of goes back to the partnership between, visual effects folks that are making the data and the people that are, training these models. Like, there's a lot of data analysis that needs to be done to understand these things, that you're not, biasing with weird little things that have been introduced into your data set along the way. So I don't know that I've encountered that exact case, but certainly those are considerations that go into, the collaboration there, as you look to understand like how well things are performing at scale. We have, in this case, we have 14 Xrays, but certainly as we would scale that data set, we'd make sure that we're not introducing unintentionally anything like that. So, yeah.
Thank you.
It seems to me like that's where your confidence level will continue to improve, right? Over time.
You talked a little bit about biasing in the beginning. I was wondering if there are any cyclical functions like sine or cosine that inadvertently line up with different offsets, and how you can kind of avoid those combinations.
That's definitely an interesting challenge, because machine learning models, if you use random patterns of any kind, they will find them. So yeah, I think that just comes down to the artistic abilities to scale data sets, and that's where it's a little bit different from VFX or game pipelines. It's procedural in a way that is diverse, I guess. I don't know if that really answers the question, but
I think the thing too is there are cases where you may want to bias your data set. If you're having a very targeted use case that you don't need to care about particular variables, and you want to overfit to something intentionally, that could be a decision that you would make. But it really depends on the end result you're trying to achieve.
And another question, with a ton of steps, like nodes in your network to create, complex forms, how do you manage the time complexity with the actual geometry or volume creation and your rendering time?
So in the case of this, it's fairly quick, and this was one iteration because we, as John said, had done this in our previous pipeline, and this was sort of a benchmark of our new pipeline. And I previously had done a lot of this in volumes, which the end result of this is volumes, but this time it's all done with geometry shaping, and then those are made into volumes, and the math comes from that. It's relatively simple pipeline, but you still need 1 voxel per pixel that you render. And so there are a few gigs per mouth, but each mouth has a set of 14 images, so you can then get a lot of variation that scales on top of that. The rendering time is almost negligible because they're unlit volumes. It's pretty much the default volume shader in Karma. So it writes the volume to disk, then reads it in, renders it 14 times, and that part is quick. But yeah, for other things, everything is managed by one main seed from PDG. There's 2 seeds that come from our pipeline. It's just at seed and then at variant seed. So the seed is driven per frame, and it's unique per frame, per variant, and then there's one seed that's just per variant. So if you want to maintain the same thing for a sequence, like if you have humans that you're varying and you're rendering a sequence for those, you probably don't want them to change every frame.
Honestly, the longest part of the pipeline is just caching out each individual VDB as we generate them. So
Yeah.
everything else runs lickety split. So
Thank you.
Hey, thanks for the interesting talk. I'm wondering if there is any methodology for finding the differences in the domain gap. So let's say you do your synthetic data, you do your model, then you evaluate it and nothing works, and you do your graphs and you look at it, but you can't notice any differences. Is there any methodology for automatically pointing out what is missing, what is the difference?
it's a really good question. It's actually an area of like deep research too. I think like there are some interesting like tools out there where you can start to identify like a heat map associated with what the model is queuing on to make a detection. That's like probably like some of the more advanced things that I personally have seen. There may be a lot other out there, but yeah, I mean, certainly a lot of time is spent in just trying to diagnose, what that gap could be. And this is where like analytical tools like the ones we showed here can help to just point you in the right direction. And then, I mean, we've gotten to cases before where it's like, yeah, we're banging our heads up against the wall. We can't understand what's going on here. And that's where we get into a stage of like, we're going to change like one thing, and then we're going to change one more thing, and we're going to try and get any signal about like what may be going on here. So it's really that iterative process that helps diagnose it, because it's not always obvious, honestly. Like there was a case we had a couple of years back where literally the model wouldn't detect anything in the real data until we added like one specific like multicolor noise to the synthetic data, and then suddenly it worked. So it's definitely not easy.
Yeah, and like I said, it will pick up on patterns. So if there's some sensor noise that you may not visually see in the render, it might pick that up as a pattern. Things like using scopes and histograms are really useful, because specifically for 2D machine learning like this, all it has is the RGB values. So just taking an analytical approach to that, I guess, is useful.
Great. Thanks so much, guys. Thank you.
Yeah. Thanks, everybody.